Okay, so section 1.3, lines, planes, and the cross product. So that's the other multiplication. So the cross product is actually only, you can only do that in R3. There's no such thing as a cross product for other dimensions. And what it gives you this time, so the dot product gives you a scalar, like a number, and the cross product gives you a vector. And the vector that it gives you is orthogonal to both u and v. So when we're in 3 dimensions, and you have 2 vectors, okay, so I'm going to, this is going to be hard to see on a video, but, so, say we have two vectors, okay? Say these pens are 2 vectors, okay? So picture that. You need 2 vectors to make a plane. So a plane is like a piece of paper. So if I have 2 vectors, I can rest, I'll show you my notes, I can rest a piece of paper, so this doesn't look like anything on the video, but I can rest a piece of paper on it, and it will hold it up. Do you agree? That's a plane. So when you're defining a plane, you need 2 vectors. Now, how many points do we need to have 2 vectors? 3 points, because each vector needs 2. Now, they don't need to be connected like at 0, 0. They just need to be anywhere. Parallel vectors would also hold up a piece of paper, right? But we need 2 vectors. If you only had 1 vector, then it's considered a line. So you can picture that piece of paper, if I set it on top, would sort of flop over, because it would only hold up a line instead of a whole plane, okay? So you need 2 vectors. Now, the cross product takes those 2 vectors and finds a 3rd vector that sticks straight out of that plane. So, can you picture that? So you've got a piece of paper, which is your plane, and then it's giving you the vector that's coming straight out of that. So it says it's perpendicular to both of the vectors, because both of the vectors are lying right on the piece of paper, and this sticks straight out from it. So it's perpendicular to both. So when you need to find a vector that's perpendicular, you do the cross product. Okay? So there's 2 vectors, and when we do the cross product, we're getting, when we don't need to draw it right here at the same place, but it's a perpendicular vector. So it's, and you can't see that in R3, see, it doesn't look perpendicular? But basically, you've got a sheet, and the vector coming straight out of that, you can see it better this way. If I draw the 2 vectors, it's harder to see. But you've got 2 vectors in the plane somewhere, and this is the cross product. These are u and v. Okay, does that make sense? So when we do that, so there's a method to find the cross product. And we actually are going to use this method later in the course to find what's called the determinant, which is something else to do with it. Yep.
Does the cross product have 2 directions?
Yeah, it could be going the opposite direction as well, and it could be twice as long, or so everyone in the class could write a different vector, because even if you make that one twice as long, or sticking out of the page going down instead of up, it's still perpendicular to the vector in the plane. Yeah. So there's not a unique vector, but every vector parallel to that vector is also perpendicular to. Right, so you can do a multiple. If you did the cross product formula and you got fractions, you could multiply it all by 100 and make them into whole numbers, right? And it would still be perpendicular. So you're not sort of stuck with that vector, because it doesn't matter the length. If you're trying to find a vector perpendicular, you can make it twice as long, 3 times as long, 100 times as long, or change all the signs, and it's still perpendicular. Okay. So we're going to do it with an example, so instead of just letters and get a great big formula. So the cross product is this. So u cross v, let's say find u cross v if u is 2 minus 1, 3, and v is 4, 1, 1. So this is a single absolute value line, which again doesn't mean absolute value. We're going to put an IJK here. Okay, I'll tell you what they mean after. Then you have to put them in the right order because the cross product is not commutative. You can't do it the other way, or you get that, well, you get the opposite sign actually. You'll still get a vector perpendicular, but you won't get the right cross product. So you can't switch them around. We'll write that down in the properties later, that they're not commutative. So you need to write U first, which goes this way. So you put U in here, and then you put V in here. Okay, do you see it? And there's going to be some crossing going on. So the method is this. This is going to get messy, and I wish I had a highlighter or something. Okay, so I is here. What you do, and you don't want to do this dark because we need the numbers, we're not crossing them out. You have a highlighter? I'm going to borrow your highlighter because I still want to see the numbers under, and I don't want you guys crossing out on the numbers. So I circled the I. So you ignore everything in the column and row that the I's in, right? But I'm going to use it later, so I didn't want it to disappear. These four numbers are what you're going to write down. -1, 3, 1, 1. Minus J, so the second one is negative. And then we're going to do the same thing for J and get the four numbers that you don't cross off. So for J, we would cross off this row, and now we want these two, you see? So we're not looking in that J. So here we want 2, 3, 4, 1. And then plus K, and then do the same thing for K. Yep.
How did you know that J was negative?
Oh, that's the formula. That is totally just the formula. There's sort of a reason later on, but each position in a matrix has a sign, but that'll just make it confusing right now. So just remember that it's the formula for now, and when we do matrices later, I shouldn't have put those little pink marks here. So if we cross off the stuff in the K, we have 2, -1, 4, 1. So the important part is you go plus I, and then your little submatrix, minus J, and then plus K. Okay? So that's the formula, and you cross them off to get what goes in these little. Okay? Those are straight lines around them, because that's a symbol for determinant, which is a cross product, which we're going to see later. So forget the word determinant. We have a whole chapter on it later, whole section. But the symbol will be the same. They call it something different here and then, but we're actually doing the same thing twice. Okay, it just means something different. All right, so now what? Now we do the cross part. So, the cross this is called the positive diagonal. So starting in that top corner, you take these two numbers and multiply them. So -1 times 1, and then subtract these two numbers going backwards. That's the cross part, you see? So positive going down, and then minus backwards, 3, 1. Whatever this number is your first element in your vector. Then minus J, and we do the same thing, cross. The first one is 2 times 1 minus 3 times 4. Plus K, forward, 2 times 1, and backwards, minus 1 times 4. So, minus 4i plus 10j plus 6k. Alright. So, I showed you two ways to write a vector, and that was the triangle brackets. The other way was up and down, like a column, with the square brackets. This is the third way with ij and k. So ij and k we've actually defined, but I didn't tell you it was called ij and k until right now. So I, the vector I, is 1, 0, 0. J is 0, 1, 0. And k is 0, 0, 1. Do you remember what those are called? The standard basis vectors. So if you think about this, if these are in here, we did this last class, what do you end up getting? The first element is going to be a 4. And from the second, this is a linear combination, if you want to remember the word. The second one is a 10, and the third one is a 6. When you add all these together, you get minus 4, 10, 6. Okay, we'll do it again, don't worry. But that vector, minus 4, 10, 6, is the cross product. Cross product gives you a vector. That vector is perpendicular to both u and v. How could we check that? Right, by the dot product. So, to check if something's perpendicular, so if a question says, to check if something's perpendicular, you always take the dot product and set it equal to 0. Some questions will give you vectors with a missing number in it, like they'll put an x somewhere in the vector, and then say what value of x makes them perpendicular. What would you do? Dot product, set it equal to 0. Right, so anytime you see perpendicular, you have to think right away, probably have to do where dot product set it equal to 0 somewhere in there. So here I'm saying u dot with the cross product. So u is 2 minus 1, 3. And if we dot that with minus 4, 10, 6, hopefully, if I didn't make a mistake, we'll get 0. So this is 2 times minus 4. Plus negative 1 times 10, plus 3 times 6. And then the same thing, v dot u cross v will also be equal to 0. And remember, the cross product is a scalar, so you get just a number. Could I have written u cross v dot u and gotten the same thing? Yes, because the dot product is commutative. We can do it either way and get the same answer. Yeah.
Why is it v dot v?
Well, I was checking if the vector u was orthogonal or perpendicular to this vector, right? This was the whole vector. If you gave it another name like W, then it would just said U dot W. And then I was checking if V was perpendicular to that. Yeah. Does that make sense? And you could have done the dot products in reverse. It wouldn't have mattered. What you can't write in reverse is a cross product. V cross U is not the same, although it just gives you the negative of the vector. So it would also be perpendicular. It would work, but if you're using U cross V, you can't just change and say now this is V cross U, because you'd have to change the signs. Okay, so they do give the same, but it's just in the opposite direction. Okay, so we'll go back and do more of these, because when we get into planes, this means something with planes. So we'll do more examples with a cross product in a little bit. We're going to jump to lines. So what's the difference between a line and a vector? A line, right, so a vector has a length, and a line is infinite. It goes in both directions forever. The arrows on the end of a line actually mean that it continues, right? So a vector, though, isn't a line. A vector is just a direction. A line is fixed in space, like it's stuck somewhere. So it has a position and a direction, where a vector is just a direction. You remember, you can pick it up and move it around, and it's still the same vector. It doesn't have to be stuck somewhere. A line is stuck somewhere. So a line has a position, like it's stuck to a point. Let's write that down. Really mathematical sounding. Stuck to a point. And a direction. Think of it as the slope. Right? When you did linear equations, y equals mx plus b, you need a point that it's stuck to and a slope, how steep the line is. Right? So it's no different here, except we're going to write them a different way. So to write a line in standard form, y equals mx plus b, that's what we normally see, right? A slope and a point, the y-intercept, or y minus y1. For both of these, we have a slope, that's the direction, right? Or we'll use the vector to do that, a slope and a point. Here the point 0b. In this form, the slope is m as well, but the point here is x1, y1, right? But they both have a slope and a point. So that's what this is, a position, that's the point it's stuck to in space, m in a direction. Okay, this is in R2. We could also have a line on a plane, right, in R3 or in 3 dimensions. We can have a line in 3 dimensions, it doesn't have to be a plane. Okay, there's no standard form for that, so this is R2, and I'll write that down in a minute when we do R3. So R2, standard form is this, vector form of a line looks like this. Okay, are we still on the page? So, vector form looks like this. xy, that's the vector, is equal to x1, y1. What do you think that is? The point. That's the point it's stuck to. Lots of different options, because there's lots of different points on a line, but sometimes they'll give you the point they want you to use, right? Or they might give you a whole bunch of points and you pick whichever one you want. And what do you think this is? The U1, U2 is the direction vector. So that's the vector. So the direction the line is in. And this T right here is any number. So what this does to the vector is it says, instead of just this vector, say 1, 1, we can have all the possible multiples of 1, 1. And what does that do to the vector? It makes it longer in all directions, or shorter. It's saying all the possible vectors on that line, right? So you can think of it as it's the parameter that makes it go forever, right? So we say times the length, right? So this is it can be any number. It's makes the vector continue in both directions. Why both directions? Right, because it can be negative or positive. Right, so we can get any point by plugging in a specific value of t. Like if you put t as 1, then you would find a point on the line by adding them. If you put t as 0, you would get this point. If you put t as 3, you'd get another point that's on the line further out, right? 3 times that. Okay, so that's vector form, and we'll do a question with this. And then the other form that you could write a line in is called parametric form. Which is just, you have to get vector form to get parametric form. So first you find vector form, and then we did this already last class, is take the letters out of vector and put the equal sign in. So you're actually just reading across. So x is equal to x1 plus what? T times u1. It's just reading across. So the parametric form is the equations. x1 plus t times u1, and y equals y1 plus t times u2. So they're just the equations taken out of the vectors. So if it says, like, find the parametric form of the equation of the line, you'd first do vector form and then just take them out. Okay, so let's do an example. Find the equation of the line through -1, 3, and 2, 1 in standard vector and parametric form. Standard form in lines is nothing new. Just regular finding the equation of lines. So we'll do that. You find the slope and use the point. So standard form. We already know how to do this. I use y minus y1 is equal to m onto x minus x1. Find the slope. So whatever point, whatever order we take the points in. So 1 minus 3, 2 minus a minus 1. So our slope is negative 2/3. And then we just plug it in. So this is nothing new. What point do we use? Yeah, either point. And so the point, let's use negative 1, 3, but you can use either point. So y minus 3 is equal to negative 2/3 onto x minus a minus 1. I just filled it in and I worked it out, and I don't think I skipped any steps, so you should be able to follow. Looks okay? Now vector form. So we don't find the slope, what do we need to find? So instead of the slope, you're looking for the vector between the 2 points. That'll give you your direction. So how do you do a vector between 2 points? You subtract them. Does it matter which direction we go? No, because we're on the line and we want both directions anyway, because we want the vector to go forever. So, for vector form, I'm just going to write down the 2 points here. So if we had the point, I'm just going to give them a name so that I can rewrite just A and B instead. Okay, so we'll give them a name. And we want the vector between them, A, B, or BA, it doesn't really matter. But once you write it down, which direction you're going, you have to subtract it the right way. So if you go A, B, then you subtract B minus A. So B minus A. And remember to switch your bracket, because we're finding the vector. So 2 minus a minus 1, 3. 1 minus 3, 1 minus 3, negative 2. Look at the slope up here. Is it related? Yeah, remember this is x and this is y. Which way is this? X, y? Do you see how they're related? They are the same thing. Because on a slope you count over, rise and run, and this is the same thing. We're counting over 3 and down 2, right? So in R2, they're related. In R3, there's no standard form, so there's no slope, so it's only a vector to get a line in R3. So in R2, though, you can actually see, and you could have just jumped to that, or if you were given the slope, you could do it. Now, what if we said 2 over negative 3 and had the opposite signs here? Would that be okay? Yes. It's the vector going in the opposite direction, which is still on that, right? If we had subtracted this the other way, we would have had the signs opposite, right? So it's still okay. So yeah, the sign doesn't matter. And in fact, you don't even need to use this vector. We could use any multiple of this vector in the equation because we want it to go forever. It doesn't have a length. All right, so this is all we need because then we set up our equation. This is our point, plus our parameter times our vector. So this is just xy equals a point. We can pick either point. Again, it doesn't matter which one, because they're both on the line. T and our vector. So this is vector form. And what's parametric form? We don't need to do anything else. Once you have vector form, you have parametric form, you just have to take the brackets out. So this would be x equals -1 plus t times 3, or 3t, and y equals 3 minus 2t. That's called parametric form. Sometimes they'll say t is free, which just means it can be anything. Okay, so it's just a different way to find a line. It's the exact same line if we were to draw it. It's just a different way. You would start at this point, you draw that point, and then you go over 3 and down 2 to get the next point, and then you draw the big line between them. It's the exact same thing. Now, up here, say we have this equation of a line. Suppose we want to find another point on the line. How do we do that if we're given the equation? Not a point we already know, but say we wanted another point. What would you do to find a point?
Plug in a value for x and find y.
Right. Plug in a value for x and find y. What would be a good value for x here?
0.
Sure, that would be easy. So if we plug in x is 0, we would get y is 0 plus 7 over 3, just 7 over 3, so we get another point. But do we have to plug in 0? No, we could plug in anything. I would probably plug in a 1 or something because there's a common denominator. So then you would just add them together and get your fraction. But anything, you could plug in 100, right? You can make a whole table of values forever and plugging in values of x and solving for y. How do you find a point on this line? I can't get the point 0, 7 over 3 really easily, or can I? Plug in a number for t. Yeah, you can't find that intercept as easily. You'd have to figure out some t that makes that top line 0, but we won't do that. So you just plug in any number. Plug in any number for t. So let's say we plug in t is 1. Okay? So what would we get? So here, minus 1 plus 3, and 3 minus 2, 2, 1. So x is 2 and y is 1. Right, that would be a point on the line. Oh, yeah, that's actually that point, which is, yeah. When I make up these equations, I actually start with the answer and then get my 2 points from it, so I obviously plugged in 1 to get that. But that gave us this point. But to find another point, just plug in a different value of t. Plug in 100, plug in -1, plug in 40, right? And then you'll solve for that. So here, what would we do? Same thing. To find a point here, let's plug in a different value. Let's say t is 2. We would get x is minus 1 plus 3 times 2. And we would get y is 3 minus 2 times 2. So that's another point on the line, right? And you can just keep going, plugging in values for t, and you would find points. So on my last final exam, there was an equation in parametric form, and it just said find 3 points on this line. I won't even tell you how poorly that question was done. All they had to do was plug in t 3 times and get different points, and people had the weirdest answers. I don't know what they were doing. I'm not saying I wouldn't put that question again, because I think it's still a reasonable question to ask, that you can take an equation and plug in a value of t and know that that's a point on the line, right? I think that's pretty okay. Okay, so that's lines. There's no such thing as planes in R2, because in R2 is what we draw in calculus. It's x and y axis, and we draw. It's just lines or points. But when we have 3D, then we have points, lines, and planes. So we'll go to R3, and we add lines in R3 and planes in R3. So, in R3, let's start with lines. So, for a line in R3, there's no such thing as standard form. So, if you're talking in R3 in 3 dimensions, and the equation has just 2 letters in it, like x and y, it's actually a plane. We saw that already earlier when the y was 0. It's like a plane going up and down. It didn't move to the left or right. It's still a plane. It's not a line when one of the letters are missing in R3. There's no standard form for lines in R3, okay? They're still planes. So, vector form. Okay, no different. It's just it has 3 numbers in the point and 3 numbers in the vector instead of 2. Right? The other is that the slope, like if you knew this, there's no such thing as slope. It's a direction. So you don't have that same relationship between the slope and the direction vector. You can't sort of match them up because there's no such thing. And then parametric form would be what? Yeah. Yep. Okay, so, and t is any number. So there's actually no difference. You would do the same thing we just did in the last example, except you add that z. Okay, so nothing is different for lines in R3. You would be given 2 points, and you find the direction between them, and then you write it out. That's all there is. So the points just have 3 in it instead. So in our 3 planes, so here we do have a standard form. Yeah, this is a 0. This is a D. Okay, I'm just going to cover it up for a second, but it'll come right back. So when we talked about lines in R2, I said standard form was y equals mx plus b, or y minus y1 equals m onto x minus x1. I use this form, and then we work it out so that it looks like that. Okay, this is the same idea. So we're going to use this form with the 0 on the end. We work it all out, rearrange it, and then it will look like that. Okay, so that's the same idea. So this is sort of the formula used to find standard form. Okay, so standard form. So we'll do that in a minute, but what do you think we need different? When we're doing a line in 2 dimensions, we need 2 points. Find the slope between them. When we need a plane in 3 dimensions, we need 3 points. Because 3 points define two vectors. We need 2 points for each vector, or 1 point in common, and then another point on each one to see the direction. Right? So we need 3 points to make 2 vectors to make 1 plane. So we need 3 points or 2 vectors. To find a plane. So you could be given 2 vectors or you could be given 3 points, and you can find a plane with either of those. So what do you think for vector form? How would it be different? Other than it has x, y, z. Okay, so this is a line. So we have a point, so it's fixed in space somewhere, the plane. And we have one direction, that makes it into a line. We need a second direction so that we can put that piece of paper on top of the 2 vectors. We need 2 vectors. So we would put plus r, another parameter, and a second vector in there. So this one would be your point. There's lots of different points on a plane, so lots of options. Sometimes they give you 3, you just pick one of them. And this is one direction. And this is a second direction. So we need 2 direction vectors and a point to make a plane. And parametric form follows from this. So here we would have t is any number, and r is any number. They could be the same number if you wanted. You could plug in r and t both as 1 or both as 0, or you could plug them in different. R is 1 and t is 2. Right? One of them is 0, one of them not a 0. And I don't have arrows on these V's and V's and U's because they're actually the components of the vector. They're not actually vectors. They're the parts in the vector, right? U is a direction vector with these numbers in it. Right. And the point, we're not putting the point in with round brackets. When you write a line in a plane, you actually put it in square brackets as if it's a vector. Okay. Which of course is confusing. Okay, so let's do find equation of a plane. This is where we start. You have to use the cross product to get the standard form. So in R2, when we find the slope using the slope formula, in R3 we have to use a cross product of 2 vectors to get sort of that same slope thing, which is the ABC up here. So we're going to do that. So the question is this. So if I give you two vectors, that's actually easier. Two vectors and a point, that's easier. 3 points is a little more work. So step one, if we want to find any of the forms, is we need to have two direction vectors. So first, find two direction vectors. There's all these different options, but we only need two, right? But I want to write this out once at least to say, like, my answer, I usually put a little note beside it, and is that you could have had different vectors than me if you had subtracted different points, right? And if you'd subtracted them in a different order than me, right? There's 6 options here, but we only need 2. I usually just don't even look at the numbers and just go A, B, and AC. That's what I usually just do, those two. So if you do A, B, and AC, you'll have the same answer as me. But if you do any of the other ones or any of the other order, your answer will be slightly different, right? If you reverse these, you'd have different signs than me, right? It's still the same plane because we're still finding, right? We can take any of these vectors and they are in the same plane because they're connected to that triangle, right? 3 points make a triangle. Think of sitting a paper on that triangle. Doesn't matter which vector, they're all in the plane, right? So AB, you have to subtract B minus A. Two minus 2, 0. C minus A. So you're basically done both vector and parametric form once you have two vectors, because you just write it out. So vector form is x, y, z is equal to a point plus t times one of your directions plus r times another direction. Sometimes they put s instead of r in the book, but I don't like s because it looks like a 5. And then people get all messed up because they think they wrote 5 when they put an s. So I know some books put s instead of r. The letter itself doesn't matter because they just represent anything. So what goes here is a point. So which point do we want to use? A. Okay. And then I usually say, could use B or C, right? And that's what I usually do on my solutions. It doesn't matter which point. And then your directions. And then I usually say, or any of the other I just usually say that, like, to remind you. You could have done different ones than me, so. Right, there were 6 possibilities. I just did 2 of them. So that's vector form. So you find the 2 vectors and just make sure you don't put points in where the vectors are. That has to be a point, and these are the vectors. And parametric form. Just take them out of that. So this is 0 plus 3t. Plus 4r, so you don't need to show the 0. The second one will give y equals 1 minus 2t minus 3r. And the third one, 2, 0t, so we don't need to put that, minus 2r. So what if you needed to find a point on the plane? Another point on the plane, what would you do? Plug in T&R, and they could be anything. They could be the same two numbers, or different numbers, or both zeros, or both ones, or one 100 and the other one 0.5. It doesn't matter. Any R and T. They can be any value. Okay, so standard form. So to find standard form, instead of the slope, we use what's called the normal vector. Okay. So we need the normal vector, which is denoted with an N instead of M for slope. In 3D, it's an N for normal. And the normal vector is a vector perpendicular to the plane. So, we've got our plane, which we don't know the equation for, and we need to know this vector, which is called the normal vector sticking up from the plane. So how do we find that? So the cross product is perpendicular to the plane. So the normal vector in terms of our formula is the vector A, B, C. And the point is x1, y1, z1, which we're usually given 3 points if we're doing this, or 1 point and 2 vectors. And our formula equals 0. Okay, so that was our formula. So we need to find the normal vector and a point, which is given, and we plug them in. So the points that we had were and that's why I said this is sort of confusing, because we called the points ABC, but they're not the ABC that's in the formula. Do you see that? These are the points that had a name ABC, but the actual formula uses that as the normal vector, right? So these are different ABCs, so be careful of that, right? Right. So sometimes they'll write the points, they'll call it P1, P2, and P3, point 1, point 2, point 3, which is less confusing, obviously. Right, but I just want to point that out, because the normal vector, they usually use capital letters ABC, but those are standard letters to use as points as well. So be careful of that. Okay, so we found two vectors, AB, we already found them, so I'll just write them down. AB was 3 minus 2, 0, and AC 4 minus 3 minus 2. Okay, so we found, and they could have been any of the 6 vectors, but we found those already, and we're going to do the cross product. So the normal is the cross product AB cross AC. I, J, K, and I wrote them in this order, so I'll put them in that order. So 3 minus 2, 0, they go across. 4 minus 3 minus 2. And then we need the I minus J plus K. So that's sort of like the formula. Those are brackets to put the 4, right? We're going to put the 4 little determinants in there. So for I, cross off the I, and we have minus 2, 0, minus 3, minus 2. You can do that. For the J, 3, 0, 4, minus 2. And for the K, 3 minus 2, 4 minus 3. And the J is negative, that's important. And then we do the cross. So the cross is positive, negative 2 times negative 2. You could just put the number in 4 if you multiply them. Be careful going backwards with the negatives. Sometimes if there's 3 negatives, that's a negative, but people will put positive. So be careful going backwards, because this one is negative, and then whatever the 2 numbers are there, which is just 0 in this case. So I is 4 minus 0. So J, 3 times minus 2, minus 0 times 4. And K, 3 times minus 3, minus negative 2 times 4. So for I we have 4. J we have positive 6. And K we have negative 1. So our vector is 4, 6, negative 1. Just the IJK was 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you don't need to do this. You can just take the numbers that are in front of each of them, and that makes your vector. So you don't need to, but that's where it comes from. Going backwards. Okay, so what next?